Hello, this presentation is about two projects I have proposed to SingularityNET's Deep Funding Round 1 and which both got accepted. I want to say a big thank you to everyone who took the time to read my proposals and to cast their votes, and I'm very grateful and excited that I get a chance to work on these projects. The first one is called Grammar-Guided Genetic Programming, which is the name for a set of methods from the field of evolutionary computation and which can be used to evolve programs in any context-free language, and this includes most modern programming languages. The plan is to implement 5 different methods from this field, which are state-of-the-art, then collect some benchmarks to compare their performance, and ultimately provide the best performing method as service on SingularityNET. And with this service you can implement various use cases. One thing could be the animations that you see on this slide, where semi-transparent triangles are evolved in order to resemble a target image. But another use case with more economic value is proposal number 2, and is called evolutionary search for robust trading strategies. The goal is to take data and preferences from a user, such as some historical market data, some indicators that the user likes, and then try to evolve meaningful buy and sell signals that lead to good returns. And the hope is that with proper modern statistical evaluation methods, you can ensure or make it more likely that what worked well on historical data will also work well on future data. Now in the next few minutes I want to give a deeper introduction into both projects and try to make it interesting for both the technical and non-technical audience. To begin with, I want to split up the complicated title of proposal number 1 into 2 independent parts. The first one is about formal grammars, and they are used to define formal languages. And with this I want to answer the question, how are programming languages actually defined in practice? And it shall even enable you to define your own simple languages, which is possible with the prototype I have developed and already uploaded to GitHub, so you can get started right ahead. The second part is about genetic programming, which is a type of evolutionary algorithm, and here I want to give you an idea how it is possible that an algorithm can evolve programs, because it's a bit simpler than you might expect. And the third question I want to cover with the presentation is, what can this method be used for? The main thing is proposal 2, but there are many other things that you can do, and I hope to show it to you in some live coding examples. So I want to start with a simple question, namely, what languages are there? And a basic distinction one can make is into natural languages that humans speak, and on the other hand, formal languages that humans create for specific purposes, which are very exact and have little ambiguity. Natural languages are studied by linguistics and can be divided into different families like those listed here. And you can do a similar thing for formal languages, divide them into groups, and you may know some programming languages like C++ and Rust that are compiled into machine code, or Python and JavaScript that are interpreted by a virtual machine. Then there are markup languages, for example HTML drives the modern web, and different data languages where, for example, SQL is used frequently in databases to store and retrieve data. Beyond that, there are also other formal languages, like in mathematics you have sentential logic and predicate logic, but that's beyond the purpose of this presentation. The next question I want to cover is how to describe and analyze languages. There are many different levels on which this can be done, but the 2 most important ones are the syntax and semantics of a language, or in other words, its form and meaning. I will only cover the syntax level here, which is usually described by a grammar. You can think of a grammar as a set of rules or constraints that tell you how small units like words can be combined into larger units such as phrases or sentences. Again, we can divide between the natural and formal area, where grammars of natural languages come in two big categories. There are the traditional approaches that sometimes go back thousands of years and which usually describe a single language like Sanskrit, Spanish, and so on. And then there are more modern variants which emerged in the 20th century and which often describe different languages or can be applied to different languages and have some overlap with formal grammars because they tend to be more precise and formal. And in the area of formal grammars, we can also identify various groups, but the two most well-known ones are constituency grammars and dependency grammars. And for the purpose of this talk and for defining programming languages, the so-called phrase structure grammars by Noam Chomsky are the most important ones, and when we will have a look at them in a minute. From here on, we take a step away from natural languages and take a deeper look at formal languages. The scientific discipline that studies them is called formal language theory, and it belongs to theoretical computer science, mathematics, linguistics, and some other disciplines. So it's really an interdisciplinary topic. There are many textbooks on it, but three quite well-known and good ones are the ones that I show here. And if you happen to be more interested in these topics, then I can recommend them as a starting point. So the next thing I want to do is try and condense the essential concepts of formal language theory into one slide, which is possible because most of them are very simple. We begin with the notion of a set, which comes from mathematics, and it is a collection of different objects. You can think of a set as a bag where you can put in anything that you want to, but there is an important restriction, namely you are not allowed to put in the same object twice because each element of the set needs to be unique. The next notion is that of an alphabet, which is a finite set of symbols, and here it differs from a set because a set may be infinite. An example of an alphabet would be the binary alphabet that consists of the symbols 0 and 1, or the alphanumeric alphabet that consists of the digits 0 to 9 and letters A to C in lower and uppercase. So an alphabet is very similar to what we understand in everyday language. You know the Latin alphabet with 26 letters. You know other alphabets which have different number of symbols and different forms. But there is one complication in formal language theory, namely that a symbol may also be a combination of multiple letters, but that's not so important for now. So the next notion is that of a string, which is again a finite sequence of symbols from one alphabet. And an example of a string would be the binary string formed over the binary alphabet, which means that it may only use the symbols 0 and 1 in it. Another example would be an alphanumeric string, which looks more interesting for humans. And you can think of a string as the content of a text file. If you write a text file and store it, then you have created a file and essentially one string. And if that string happens to be part of the, let's say, C++ programming language, then you can compile that file. If that string happens to not be a part of that language, then the compiler will say that you have made a syntax error and that means that the string does not belong to the C++ language. That brings us to the central notion, which is a formal language itself. And it is very simply a set of strings over one alphabet. And importantly, it does not need to be finite. So it might be an infinite or unbounded set of strings. And an example for such an infinite language would be this binary language here, where each string starts with one or more zeros and ends with a 1. A simpler language would be this example of an alphanumeric language, which has 3 elements and is therefore a finite language. And the central question in formal language theory is how you can define infinite languages, because the finite case is very simple. You can just list all elements. In the infinite case, you need some system, some formalism that is able to say for an unbounded number of strings whether they belong to the language or not. And the two main systems we have for that are formal grammars and automata. Those are systems we frequently use to define languages, and every higher level programming language that is in use today, or most of them, are defined by some formal grammar. And we will see an example of that later. Now I hope that was not too fast and you got a basic idea what a formal language is and why we need formal grammars to define them. And the next thing I want to do is introduce the Chomsky hierarchy, which identifies 4 different kinds of grammars, and they can generate different classes of languages. So I will start with the languages. On the bottom you can see the regular languages, which are the simplest ones. Then come the context-free languages, the context-sensitive languages, and the recursively enumerable languages. The last one is the most comprehensive set of languages and actually contains all others. This is why it's called a hierarchy. It's a containment hierarchy. And the grammars that can generate these languages are called the regular, context-free, context-sensitive, and unrestricted grammars. And they differ by the ways that their rules are constructed. The rules of a regular grammar are quite restricted in their form, while the unrestricted grammars have rules that can do a symbol manipulation in all ways that are possible. So it can replace any pattern with any other pattern you can imagine. And I mentioned automata. There are actually 4 automata that can recognize exactly the same languages. And again, on the bottom, the finite state machines are the simplest ones, and on the top, the Turing machine is the most complex one and can recognize any formal language that you can define. There is also a difference in these languages in how fast you can recognize if a given string belongs to the language or not. And this is the reason why in computer science we usually are restricted to regular and context-free languages, because for them it's possible to quite quickly recognize the structure of a given string, while in the other cases it would take much longer, and therefore they are not as often used. With this, we have arrived at a point where I can explain how modern programming languages are usually defined, namely by a context-free grammar, and I will introduce it by an example. Here you see a grammar which consists of 5 rules. Each rule is a prescription how you can transform or rewrite the symbol on the left-hand side of an arrow to the sequence of symbols on the right-hand side of an arrow. And you can see 2 different kinds of symbols here. The uppercase black letters are so-called non-terminal symbols. You can think of them as placeholders or variables that can still be transformed into something else. The green symbols are the terminal symbols, which become part of the string that the grammar can generate, and they form the alphabet of the language that the grammar defines. And we also need a start symbol, which is a non-terminal and usually the one on the left-hand side of the first rule. So what we can do with the grammar is we can derive different strings, all strings that belong to a language. And here is an example of such a derivation. We start with the start symbol S, we use the first rule and replace S by the sequence letter, digit, digit. Then we apply the second rule and transform the letter non-terminal into the terminal A. Then we use rule 4 and 5 and replace the digits by terminal symbols. And A21 is now a string of the language that the grammar has defined. And if you would use different decisions along the derivation, you would get all possible strings that this grammar can generate. Okay, with all that knowledge, we can now jump into a live example, and I have promised you that you will learn how to define your own simple formal language, and we will do so with the package that I have uploaded to GitHub, which contains 2 out of the 5 methods that I want to implement, and this is an improved version of the prototype that I've used for the proposals. You can install it with pip with a simple one-line command. Importing the package looks like this. I've called it Alogos for a library of grammatical optimization systems, and we will define a grammar in what is called extended Bacchus now form, which looks like this. We had our start symbol that can be transformed into letter, digit, digit. Then we had letter that can be transformed into the terminal A. Then we had also as option that the letter can be transformed into B. And one possibility to make it shorter is that we can combine two rules onto one line, which looks like this. Now we are missing digit, which can be transformed into 1 or into 2. So this is the text that defines the grammar. Now we need the grammar class from my package. And this is what the grammar object looks like, a visualization of all the rules that are contained in it. And we can use it to generate random strings. This would be some examples. But we can also use it to generate the entire language, which looks like this. So there are 8 different strings in the formal language that we have defined by this simple grammar we also had on the slides. And one more thing that we can do that I have not shown you before is that a grammar can not only generate strings, but it can also recognize and even analyze the structure of strings. So what we get here is a derivation tree or parse tree, and this looks like that. This is another way how to depict a derivation. The symbol S is transformed into letter, digit, digit. Letter is transformed into A, digit is transformed into 1, and the other digit is transformed into 2. What I want to do now is make a big jump from the toy example I've just shown you to learn the basics to a real-world grammar. This is the grammar that defines the Python programming language, and it's written down in a mix of extended Bacchus now form and parser expression grammar. But this is just a notational thing, it's still a context-free grammar, as far as I know. And I just want to give you an impression how large such a thing looks in practice. There are a lot of non-terminals and a lot of rules, and actually this is not the entire thing, because some placeholders are not defined here and numbers are defined elsewhere. And what I want to show you are the integer numbers that you can type inside a Python program. This is again a grammar in extended Bacchus now form that defines the integers in Python, and you can actually use that with my package, which I will show you here. So we can generate random Python numbers. And some of them, or most of them, look quite weird. This, for example, is a binary number and the number 0. This is a hexadecimal number and should be the number 15, and we can try that. If you evaluate it, oh, it's 14. Yeah, that's right. And in this case, we have an example of an infinite language. There are infinitely many Python integers that you can type. And you cannot generate the whole language, of course, but you can say that you want to try all derivations with a maximum step size of, let's say, 5, and then you get the strings that can be reached with that. And so here are a lot of different integers that you can reach, and we can pick a binary integer and add it with, let's say, some hexadecimal integer. And it should work. Yes, it evaluates to decimal 13. So now that I've spent quite some time to explain what formal grammars are, I want to very briefly mention what genetic programming is about. It's essentially an optimization technique, and optimization means that you are looking for the best option out of many available ones, or sometimes it's okay if you find a good option. And the easiest way to do so is that you try to assign a score to each option or candidate and simply choose the one that has the highest or the lowest score depending on what means best in your case. Optimization problems come in 2 basic flavors, the continuous and discrete ones. Continuous means that the candidates' variables can be chosen arbitrarily fine, and what you get is what is sometimes called a fitness landscape, where you can use concepts from analysis to very quickly find your way towards the lowest point of the parameter configurations. And this is very important in deep neural networks. The other flavor are the discrete optimization problems, where the traveling salesman problem is very famous. And there the task is that you have a bunch of cities and want to visit each of them once on the shortest possible route that leads you back home afterwards. So you have a lot of possible routes as candidates, you assign a score which could be just the length, and then you use the route that is the smallest one or the shortest one. And that's a very hard problem to solve. You can only do it with approximations, and evolutionary algorithms are powerful techniques that can solve all sorts of such difficult optimization problems, especially the discrete ones. So evolutionary algorithms are actually quite old. They were invented independently by 3 different groups in the 1960s and 70s, of which probably John Holland is best known for his genetic algorithms. A bit later, genetic programming was developed in the 80s and 90s, and during that time the field also got unified into a single framework, and today it's the field of evolutionary computation, and every algorithm is called evolutionary algorithm. Now, the classical genetic programming has the disadvantage that it usually was quite limited and only worked in a single language such as Lisp, while the more modern variants such as grammar-guided genetic programming, the topic of this project, are less limited. They can evolve programs in any language, and you can express search spaces quite freely as a user. And I've listed the 5 methods that I want to implement here in this project. Some are a bit older but are quite popular, while some are quite modern, and I want to compare them and provide them on the SingularityNET platform. On this next and final slide, I want to give you an idea what an evolutionary algorithm looks like. It's essentially inspired by nature and the process of natural evolution. And this is a bit similar to neural networks, which are also inspired by nature and structures you can find in it. But in both cases, it's important to say that evolutionary algorithms and neural networks have very little in common to the things that exist out there in nature. They are more metaphors and not so much a representation of what is going on out there. So the idea of natural evolution is that you have a population of individuals that compete for survival and reproduction. And the ones that succeed better in it, they are said to have a higher fitness. So individuals with higher fitness are better adapted to their environment, and therefore they can survive longer and generate more offspring. And this is a process that happens repeatedly, and thereby you get populations that have increasingly better fitness. They are increasingly better adapted to their environments. And a similar thing you can do in an algorithm, where you start with generating an initial population of candidate solutions. You evaluate them, which means that you assign a score to each candidate, and the better ones are selected to become parents. They are allowed to generate offspring, which happens via random variation in form of crossover and mutation. Once you have this offspring population, you also evaluate it, get new scores, and hope that they will contain some better ones. And ultimately, what you do is survivor selection. You only let individuals keep going on into the next generation that have a high score or a high fitness, and those individuals can be taken from the offspring or also from the parent population. If you repeat that via multiple generations, you hope to find candidate solutions that have higher and higher scores and are better in solving your task. So in essence, an evolutionary algorithm is a optimization process that works in a trial and error fashion and cannot guarantee that you will find the best solution, but often finds very good solutions to hard problems. And in the case of genetic programming, each individual represents a program. Evaluation means that you run the program and look if it fulfills a certain task, good or not. And crossover and mutation mean that you introduce slight variations into the program, hoping that some of these variations will lead to better programs. So to conclude my presentation, I want to give you two final code examples, a simple one to understand the concept and a real-world one, which will be the proposal number 2. I have defined here a grammar that represents a language of arithmetic expressions, which is simply a number, an operator, number, an operator followed by a number. A number may have 1 or 2 digits, and the operator may be plus, times, or minus. Let's see some strings that can be generated with it. So all of them would be arithmetic expressions that, if you evaluate them, give a certain number. Let's try this one. This evaluates to minus 88. And what we want to do now is find an optimal string in the language of the grammar, but in order to be able to do so, we need to define a goal. And we could say that we want to find an arithmetic expression that evaluates to a certain target number. The way we can do this is we define an objective function that gets a string as input and needs to return a score as output. And the easiest way how we can construct a score is we evaluate the string to get the number that the arithmetic expression represents, and then we say we return the deviation from the target number. What we want to do then is we want the evolutionary algorithm to find an arithmetic expression that minimizes the objective function, that minimizes the deviation from the target number. So the grammar is the search space, or the language of the grammar is the search space. The objective function tells what is our goal, and then you can say that you want to find the minimum or the maximum score according to that goal. So let's try this. Okay, it found a solution, and let's check if that's a correct one. Yes, we have found an arithmetic expression that evaluates to the target number. And what we can also do with the grammar is we can look into how this string is generated. We have the start symbol, number, operator, number, and it uses 2-digit numbers and has chosen these terminal symbols. And to give you an idea how mutation and crossover can work in the case of genetic programming is you could imagine that a slight mutation would be that we exchange this decision here to use the digit 2 instead of 6. That would be a solution that is a bit worse, but if you have not yet found the optimum, then it might be a bit closer to it. And crossover would mean that you have two different arithmetic expressions and you exchange, for example, the middle tree here, the middle number. So instead of the 99, I would get a different 2-digit number from some other solution like 55 or whatever. So with all of that in mind, we can come to the final question, which was, what can grammar-guided genetic programming be used for? And one example is my attempt that I want to use it for evolving robust trading strategies. This is actually not entirely new. People have tried that and there are some publications, but usually they do it in an overly simplistic way and fall into some pitfalls that I will mention later. So a trading strategy basically is an algorithm that tells you when to buy and to sell an asset. The user can define what asset is interesting to him, or which could be from the stock market or some cryptocurrency. And you can also define what the trading strategy will be based on. So this could be different indicators like moving averages and MACD, RSI, or much more exotic ones, but also external data like price predictions or fundamental analysis. So what I've listed here are some backtesting libraries that I've found in Python. Part of the proposal is that I want to take a deeper look into what is available and decide if I want to use one of them or implement my own one. And backtesting just means that you evaluate a method on historical data. And in this case, I also use the historical data to come up with the method in the first place. And this already hints at a problem. A pitfall is that often you overfit to the historical data, which means that the strategy that you find will work well on what you have given to the algorithm, but it won't work as well in the future. And second pitfall is that you might optimize for the wrong thing. You might optimize for the maximum profit and not take into consideration that you also want to prevent major downturns. So you probably will like to have a risk-adjusted performance measure, and there are different ones out there, and part of the work for the proposal will also be to decide which ones are most suitable for my case. So the code example that already works is based on this library, and the grammar that I have used to define the search space, the space of all possible strategies, is a bit ugly. It just evolves a Python class where 4 different conditions can be used to set an action. An action can be to buy or to sell, and the conditions can be based on 4 different moving averages, which can be taken over a different amount of time that the algorithm can also choose by itself. And the objective function that I evolve here is I translate the string into a Python program, into a strategy that can be executed, and I test this strategy on the Google stock market data over 8 years or so with the backtesting library that I've chosen above. And the performance measure that I want to optimize is the Sortino ratio, which takes into consideration that you don't want to maximize your potential upside, but also minimize your potential downside. This is what a random solution looks like, where it uses some arbitrary numbers for the moving averages. This would be a 80-day moving average, a 33-day moving average, and it would say if a certain moving average crosses another one, that's a sell signal, and if that happens in future, it will sell your asset. So the evolutionary algorithm looks very similar as before. We give it a grammar and objective function, and in this case we want to maximize the Sortino ratio. We want to find a strategy that has a high value for it, and if we let it run for approximately 3 minutes, then it finds a result that looks like this. It uses moving averages with quite different window size. It generates a return that is quite high, but you need to consider that just buying and holding the Google stock would have also given you good returns. So what you want to actually take a look at is the ratio between the return that the strategy achieves on the historical data and the buy and hold return. And in this case, it finds a strategy that is 2.3 times better than if you just held the Google stock. And one more thing that I can show you here is that the number of trades over 8 years is 78, which is quite reasonable. It's not too fast or too slow. And here are some different ratios where if we would have optimized for the Sharpie ratio, then probably a different strategy would have been chosen. And part of proposal 2 is finding out which of these ratios work good, but also how you can prevent various other pitfalls of using a backtesting library. As a final note, I want to give you 2 websites where you can find more examples if you're interested. The first is a website I generated when proposing my projects, and you have some examples where I evolve Atomize code, which is the programming language of the OpenCog framework, where I evolve Meta code, which is the language of the next generation of OpenCog called Hyperon. And there are also examples where I solve problems from OpenAI Gym. And the second website is by John Kosa, who popularized genetic programming in the 1980s, and he collected what he calls human competitive examples where genetic programming or evolutionary algorithms in general were used to deliver interesting real-world results. And some of the algorithms you find on the right-hand side are those that I want to implement, such as grammatical evolution. And my goal is to make these methods available to everyone in this simple fashion and to compare them rigorously to find out which of these methods has the best chance to perform well on a new problem. And with that, I want to thank you for your attention. I hope I could give you some new insights. And I look forward to any kind of feedback and to the discussion. Thank you.